Hello everyone, I'm Jiatong. Today I will show you how to use CST Studio to design a Wi-Fi half-wavelength dipole antenna. Here I use CST student version, which is free. You can download it from CST website. For the student version, there's a limitation. The mesh cell number only support to 30K, which means we can't do very accuracy modeling. But anyway, it's free, so let's do the modeling. Accept. Here we need to create a new project. You can see for the CST Studio suite, there's 5 parts. For antenna engineer, we choose microwave, RF, and optical. Then go to antennas. You can see here's lots of different type of antenna you can choose. Like mobile phone antenna, reflector antenna. Here we want to design a dipole, so we choose wire antenna. Go to next. Then we choose time domain. Here's lots of units you can choose because Wi-Fi runs at 2.4 GHz or 5 GHz, so we don't need to change units here. So go to next. Here it asks you to set the frequency you want to investigate. Here I set 1 GHz to 10 GHz because I want to see how this dipole antenna performance at between 1 to 10 GHz. Especially see its S11, I mean return loss. Here we choose E field, H field, and the far field, and define at here 1, 2.4, and 10 GHz. Here it will give you the radiation pattern, much more details at these 3 frequency. Go to next. Name, give it a new name. Let's say Wi-Fi dipole. Finish. Okay, get into the CST now. Here is the main panel of the CST. We can design the dipole antenna in this main 3D area. Before we build the antenna, we need to set some parameter for the dipole. First is we need to know the radius of the dipole. So here we set a variable name. Dipole, let's say 1.5 millimeter. We don't need to set the unit because we have done that before. And say description, radius of dipole. Second parameter is the length of the dipole. We use L. Here is a small tips. You can calculate the dipole length. Use these small tools here. Calculate wavelength. Because our Wi-Fi dipole runs 2.4 GHz, so 2.4 GHz. Then you can get the wavelength, half wavelength, quarter wavelength. I think these tools are very useful compared to HFSS. So here we got half wavelength, 62.46 millimeter. So here 62.46 millimeter. Then length of dipole. This third parameter is about your feed, the length of your feed. So here, say 10 millimeter for the feed. Length of feed. Another parameter is impedance, your input impedance. Here, because we design is half dipole, so the impedance actually is 73 ohm, not 50 ohm. So here set input impedance. Okay, then let's build the antenna. Go to modeling. Here, choose cylinder. Give it a name, say Dipole. And the outer radius is R, X0, Y0, Z minimal minus L over 2. Here, material. Actually, you can use perfect PEC, perfect conductor, or you can choose your preferred material like Cooper. Then you can choose this Cooper wire. Here, just show you how to do that. We choose perfect conductor as an example. Then we can preview and go to OK. Here we got the main body of the half wavelength dipole. The second is you have to build the feed point. Go to another cylinder. Main feed. Actually, the half wavelength dipole will be fit in the middle of the antenna, so the radius is same. So here we set R, X0, Y is 0, minus F over 2, F over 2. And here we use 1 coulomb. Preview. See, here will be fit in the middle, and then press OK. Here we choose none to all. Like HFSS, you can add these two components together or do some substrate. So here, I'll show you. Once you click this dipole, then boolean it. Here we choose insert. Then click this feed. Press return. Then you can see here will become 1 coulomb. These two elements separately. Then we have to set the voltage. Choose this. Pick the voltage here, and pick another. And we choose this crescent point. Here is the impedance. As we said before, here we use Z instead of this 50 ohm. Okay. You can see the current is from this side through to this side. Then we can go to step slower to do the modeling now. But before that, we have to check the mesh cell. As I said, the limitation is 30K. So let's see how much we use. Here, mesh cell is, wow, 89K. So we have to reduce that cells. Close the mesh wheel and the global property. Here we change reduce the number. Let's say 5, 10. Update this parameter to see. It became 12K now. Maybe I can do a little bit more. Let's say 8. Update. Okay. Then we select step slower. Accuracy here. Well, if you choose more accuracy, it will take more time. But here we choose -40. -40 dB is fine. We then go to start. Then it will do the simulation automatically. Okay, it has done. If we want to check the result, like return loss, S11, here we can get the S parameter in the 1D result. We can see how the S parameter changes from 1 to 10 GHz, and at the moment the antenna will be resonant at roughly at 2.2 GHz. However, we want to move it to 2.4 GHz. To achieve that, we can adjust the antenna's length. Another thing is currently the S parameter, the unit is in dB, and here you can click the linear and it will change to decimal number. And also we can check the real part or imaginary part of the S parameter. We can make some marks on the curve, then we can see the result. So here, zoom in, we want to see, double click this point. You can see at 2.18 GHz, the return loss is only 0.06, which means, let's see, let's calculate, 0.06 times 0.06, so there will be 99.64% power will deliver to your antenna. This efficiency is very high. However, it's at 2.2 GHz. We have changed it to 2.4. So we have to build another parameter. Let's say A. Use this value, 2.1881 over 2.4. Then we use this value times our previous antenna length, A. So the system will ask you if you want to delete current result. We click OK. Then we do the simulation again. Start simulation. Okay, it's finished. So let's check the S parameter again. Here we got our new S parameter. After zooming in, we can see the antenna will resonate at 2.4 GHz exactly. That's what we want. We can change it to linear, then mark to check the return loss here. Double click. At 2.4 GHz, the return loss is only 0.057. We can calculate this value. Here we can see nearly 0.34% power will be delivered back from the antenna to the transmitter, which means the return loss is very low and the transmission line efficiency is very high at the moment. Also, we could check the radiation efficiency and total efficiency in 1D result. Here we got radiation efficiency, total efficiency. The difference is total efficiency equals radiation efficiency times the transmission line efficiency. It's caused the difference caused by the impedance mismatch here. Also, we could check the VSWR. You can see at 2.4 GHz, VSWR is quite low. So 2.4 at the moment is nearly at 1.13. So if the VSWR equal to 1, which means 100% power, all the power will be delivered from transmitter to the antenna. But that's the ideal case. Also, we could see some interesting results like how the E field changes in 2.4 GHz, or we can check how the H field changes here. I think these functions are very interesting because HFSS doesn't show much like that. It's very useful for beginner to understand how the E field and H field change. Also, you could check how the surface current flows. We said the feed here is positive and here is negative, so the power you can see at the two ends of the dipole, the current is 0, and in the middle point is reached to the peak value. Also, we could check the radiation pattern of our designed Wi-Fi antenna in free space. Here we got the radiation pattern in 2.4 GHz. Here we can check the 3D radiation pattern. We also could check the 2D radiation pattern. It's very convenient. And it also shows the 1 GHz radiation pattern and 10 GHz radiation pattern. Okay, that's it. If you have any question about the video, welcome to leave a message in my channel. Thanks for watching. See you next video. Bye.